Alrighty, so here's your second series on chi-squared analysis. Just to review a little bit, go back and look at our equation for obtaining the chi-squared, and just to move backwards a little bit. So, if you look, so chi-squared is equal to the sum of the differences between the the observed and the expected frequencies squared divided by the expected frequencies. So kind of working back, remember, again, this is just a refresher. Where did this come from? Well, this was the bivariate table stuff where we observed, the number of men and women who were first and non-first generation college students. And then in order to assess, so basically the chi-squared test is, comparing the observed frequencies to what we'd expect if there was no relationship at all, right? So this is what we observed. How do we calculate the expected frequencies? Well, that was where the marginals came in. Remember, to get the expected number of men, we take the row marginal times the column marginal. And then we get this right here, this frequency distribution for the expected frequencies. And then in order to get this calculation, remember, you kind of go step by step. So we do the observed number of men first, then the expected number of men first. Again, it's expected if there's no relationship. Subtract the two, square them, and divide by the expected frequency. And then we sum them all up and get the chi-squared number. So hopefully that was clear. I mean, what I did on Tuesday was certainly the most heavy lifting math and kind of equation part of it. Today is just kind of clarification and then adding another little thing to it. So keep in mind, the whole idea for the chi-squared is, again, comparing the observed to the expected. And then similar to, this should bring back memories of the, when we did the standard deviation calculation, the sequential kind of thing. And we get the, basically we kind of build our equation, right? I mean, we're looking for this eventually, the sum of the observed minus the expected squared divided by the expected. But in order to get that, you kind of have to piece it together like this. And again, this is in your book. And then we take, each of the parts, add it up, we get a chi-squared value of 58. And then depending on the level of confidence that we want, go to our chi-squared table in the back. Remember, the degrees of freedom calculation is a little bit different. Let's show you that. If I can find it. I'll get to new stuff eventually. It's just the row minus 1 times the column minus 1, and these are the attributes. So in our case, we had our two variables were sex, and then our attributes were men and women, and then generation of college student, so first and non-first. So they each have two attributes. So we do 2 minus 1 times 2 minus 1, which is going to give you 1. So in our case, we've got a degree of freedom of 1, and even you can see, even if we go up to up to a confidence level of 99.9%, we're still above. Remember, the key in both the hypothesis testing and the chi-squared testing is we calculate what's called a test statistic. So we get our test statistic, and then we compare it to a critical value. If it's above the critical value, then you reject the null, you accept the research, and you can say there's a relationship. If it does not hit the threshold, if it does not hit the critical value, so for instance, if it's less than 10.827, then we would accept the null or fail to reject it. So again, the critical values like that, I'm gonna show you visually. The idea with the critical value is it's this kind of cutoff point. And when we calculate a test statistic, if it's below that critical value, then there's no relationship. But if it ticks up above that critical value, then that's where we have a relationship. We can say that we reject the null, we accept the research hypothesis. The two variables are related. So again, it's like that critical value is like that cutoff point for innocence and guilt. So you can see, I mean, doing this a couple times, you'll get used to. If you see a chi-squared statistic of something like over 50, you can rest assured that it's significant. I mean, unless you just have a, just looking through here now, so what do we have? 58. So it wouldn't be significant. So let's if we had 30 degrees of freedom, and we're looking for a 99.9% confidence interval. See how it doesn't tick above that, so we couldn't say that. But in our case, we only have 1 degree of freedom. And at every level, I mean, we could say here's the 95% confidence level, 98, 99, 99.9. So the key really becomes comparing that test statistic to the critical value. I hope that's clear, because it's the same logic you did back, think back to hypothesis testing, and you're just doing it again here. Calculate the test statistic, compare it to the critical value. If it's less than, you can't deny the null. There's no relationship. In order to prove a relationship, you got to get above that critical value. Okay, so that's just a little refresher. That's kind of where we left off. So I'm going to use the same example that I did in these slides just to kind of illustrate the next point. So hang with me here. We with this bivariate table between sex and generation status of college students, we find a chi-squared value of 58. Okay, so on to the new stuff. So making a final decision. Okay, so you got that chi-squared value of 58. You could kind of think of it this way. So the probability of obtaining a chi-squared value of blank is less than blank. I don't know how helpful that is for you, but let's fill it in. So you would essentially say that the probability of obtaining a chi-squared value of 58, what we got, is less than your p-value of 0.001. So if these two variables were not related, getting a value of 58, you could only get that 0.001 would be the proportion, so 0.1% of the time. So another way to say it is that you're 99.9% confident that they are related. Again, these are the same things. I just kind of want to frame it in different ways. You could say that we're 99.9% confident that they are related because the critical value, because the test statistic is above this critical value. Likewise, you could say that the probability of obtaining 58, if those two were not related for our chi-squared value, is less than 0.001 or less than 0.1%, right? 0.001 is, convert that into percent is 0.1%. So we're obviously really sure. Part of the point in showing you this is that we're never 100% sure of anything. Obviously, we're 99.9% is much more confident than 95, which is more confident than 50 or whatever. But there's always a degree of uncertainty. But again, it's just the same. It's really the same thing. You could say that we're 99% confident they are related, or you could say that there's a 0.1% chance that that they're not related, and we just got this value. So obtaining that value of 58. The probability of obtaining that 58 is less than 0.001 if they weren't related. So again, if your p-value is less than alpha, then you reject the null. If your p-value is greater than alpha, then you fail to reject the null. Again, you can use, I'm saying the exact same thing just in a different way. Before, like I said, you could compare the actual chi-squared critical value to the test statistic. So the test statistic is above 58, is above 10, so it's 58, remember? So that would, so we're, in terms of like assessing our test statistic to this critical value, we're above it, right? So we would reject the null. The other way to think about that is if I said, I want to, do the chi-squared test at a point alpha equals 0.05. Well, my p-value is 0.001, right? That's obviously it's less than 0.05, so in that case, our p-value is less than alpha, so we reject the null. Again, it's the same thing. It doesn't matter if you're comparing the p-values to each other or you're comparing the test statistic and the critical value, right? So before, we had that 58 that we calculated. This is our test statistic, and then our critical value of 10.82 that we found in the book. And this one's higher, so we would reject the null. The exact same way to think, the exact same thing, it's just a different way to think about it, but literally you arrive at the same answer, is to say that our your test statistic that we found had a p-value of 0.001, right? It really would be higher than that, but that's as high as it's going to go here. So if this is our test statistic, well, our critical value that we were using was an alpha equals 0.05, or whatever I specified. Even if I specified 0.01, the point is that the p-value is less than. The only difference is that when you're comparing p-values, if your test statistic is less than the critical value, then you reject the null. If it's greater than, you fail to reject the null. In terms of actually comparing the chi-squared value, if the test statistic is greater than the critical value, which it is, we reject the null. If we would get a number, say 7, and it's less than the critical value, then we would fail to reject the null. Again, it's the same thing, it's just different ways to think about it, whichever helps you more. To be honest with you, I like to just use the chi-squared statistic and compare it to so I like to get the test statistic for chi-squared, calculate it, get that 58, and compare it to the critical value. Some people like to look at it as the p-values. Whatever you like better, you'll still arrive at the same answer. And in this example, obviously, we reject the null. We accept the research. We say that there is a relationship between sex and generational status in college, and it operates such that there are more first-generation women than men. Okay? So that's your final decision there. And here's your little, the larger the chi-squared statistic, the smaller the p-value, right? So it's like, as your test statistic goes up, 58, 59, the higher it goes, the smaller your p-value gets. And as your test statistic gets higher, so if your test statistic goes up, your p-value goes down, and your likelihood of rejecting the null, finding a relationship, goes up, right? Larger tests, and that's the same with chi-squared, it's the same with the z test statistics, same with t, it's the same with don't get hung up on these different curves. All it really is just some of them are more flexible, is really what it is. The z is the least flexible, the chi-squared is the most. And just depending on the procedure, you use different ones, but it's kind of the same. It's the same idea. They're just slightly different curves. But in terms of calculating a test statistic and comparing it to a critical value, it's the exact same thing. And larger test statistics, you're going to be more likely to reject the null. That's kind of this would sort of summarize the last 3 weeks of business that we've been looking at. So hopefully that's clear. Okay, so next thing I want to get into is an assessment of strength and direction. So if you go back to the old slides, I think the first thing I told you was that we can examine 3 aspects of the relationship. Is there a relationship? That's what your chi-squared test does. That's what we've, everything I've done up to this point on chi-squared testing, test to see if there's a relationship, right? We either reject the null and say there is, or we fail to reject the null and we say there isn't. So if we fail to reject the null, we didn't find enough evidence to say no, we can say that they're not related. So the first thing you want to do is the chi-squared test. It tells you whether there's a relationship or not. Yes or no. It's your hypothesis test. Is there a relationship? Is there not? But it doesn't really tell us anything about the strength or direction. And that's what I want to throw in today, and that's Kramer's V. And Kramer's V is a relatively easy calculation, but it's based on the chi-squared test. So the first thing you have to do in order to look at Kramer's V is to calculate the chi-squared. And it kind of makes sense because think about it. If you find a relationship like we did, so the last example, we found a relationship between generational status, generational status in college, and as our dependent variable, and then our independent variable is sex, right? So we found that relationship. The next question would be, how strong is it and in what direction. Now, obviously, if we did this test and we got a low test statistic and it didn't, surpass the critical value, and we found there was no relationship, so we failed to reject the null, no relationship, then you wouldn't do Cramer's V, because if there's not a relationship, it doesn't have strength or direction. We only assess the strength and direction if there is a relationship. So in our case, there's a relationship. We want to know how strong is it, relatively speaking. Are they really strongly related? Is it weaker? Is it moderate? And then we also want to know the direction. So the calculation for Cramer's V is actually really, really simple. All it is you take your chi-squared value, which you calculated, and then divide it by the sample size, and then times m. And m is whichever one of your marginals is the lowest, okay? So it's your degrees of freedom marginal. So, before we had 2 rows and 2 columns, right? So that's going to be exactly the same. In our case, that'll be the same. They're not smaller or larger. But imagine that we had a independent variable with 3 attributes. So independent variables go in the columns. So we'd have 3 columns, and then a dependent variable still with 2. Well, in that case, we would use the rows, because there's only 2 compared to 3. So whichever is lowest between those, and then you just subtract the 1. So it's basically like the degree of freedom of your least number of attribute variables. So again, like I said, in our case, we have a 2 by 2 table. So which one's less? They're the same. So take 2, subtract 1, and you get 1. And that's your m value. So that should be pretty straightforward. That's not always 1. It's just your, it's your number of, it's your smaller of the 2 minus 1. And I think I might have misspoke. So let's say, let's say we have a independent variable and a dependent variable. All right, that's really sloppy looking, sorry. Independent variable has 3 attributes, right? And they're in the columns. The dependent variable has 2. So here we have a 2 by 3 table. So you'd want to take the 2 because it's smaller. I think I said 3 before, but always take the smaller of the 2. Whichever value is the lowest, okay? So 3 minus 1 is 2. 2 minus 1 is 1. We take the lowest value, 1. Plug this in here, multiply it by the sample size, and divide the chi-squared value into that and take the square root, and that'll give you the Cramer's V. It's really, really straightforward. So let's go back to our example before. All right, so Cramer's V is equal to square root of the chi-squared divided by m times n, okay? So it's the square root of our chi-squared value is 58. M is the lowest of the row minus 1 versus it's the lower of the degrees of freedom of either variable. So in our case, it's 1 because they're both 1. 1 times, we get our sample size, 4620. 4620. Okay, so you just take 58 divided by 4,620, take the square root of it. Let me pull up my calculator. Go ahead and show you. So 58 divided by 4620, 0.01255, yada, 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 okay? And then we just take the square root of that. 0.012554, that's enough. Okay, so there you go. Point 112. Okay, so that's your Cramer's V. So the question is, how strong or weak or whatever is that? Well, here's your little guide. Okay. So this last slide kind of sums everything up. So that is there a relationship? That's where you use the chi-squared. Calculated test statistic compared to the critical value. Tell me if it's related or not. You either reject the null and say they are related, or you fail to reject the null and you say they're not related. If they're related, then you can go ahead and assess Cramer's V. If they're not related, there's no point in assessing the strength because there's no strength. They're not related to each other. So in order to assess the strength and direction, we use the chi-squared value, the Cramer's V equation to assess the strength and direction. And this is from your book. It's a nice little okay. So stronger relationships are going to be hot. Like, okay. The basic point is that we have this Cramer's V is only going to range from 0 to 1. And oh shoot, hold on one second. I've got someone at the door.